To anyone who has ever worked with rare earths, this is a thing of beauty.
But getting the rare earths out of that rock is nasty business, requiring toxic acids and lots of water.
The wars of the future won't be decided first by tanks crossing borders or fleets sailing into contested waters. They'll be decided much earlier, inside supply chains, chemical plants, and materials labs, buried deep inside electric vehicles, wind turbines, smartphones, and the guidance systems of the world's most advanced weapons lies a quiet set of elements that now decide who holds power and who waits for permission. Rare earths don't make headlines like oil once did, but they move missiles, turn radar arrays, and give fighter jets their edge. Control them, and you control the speed of industry, the readiness of armies, and the direction of technological dominance. For decades, China understood this reality while others looked away. However, a major US discovery might change everything. The fate of the world hangs in the balance. You don't want to miss this. China's rare earth monopoly and strategic leverage. Rare earth elements, including neodymium, dysprosium, terbium, and yttrium, are 17 in number, and despite the name, they are more common in the Earth's crust than silver.
Unusual metals that are sprinkled inside almost every piece of high tech you can think of, but we have become so reliant on rare earths.
It is only the brutal cost and complexity of getting them out of the ground and into usable form that makes them scarce. In the 1990s, while Western nations tightened environmental regulations and stepped back from heavy, polluting industries, China saw rare earths as a cornerstone of future industrial and military power. The government poured state capital into mining and, crucially, into the most complex part of the process, refining and separation. Rare earth ores are rarely found in concentrated deposits and are mixed with radioactive materials like thorium. Yet China accepted that dirty business when others would not. By offering subsidies, cheap labor, and lax environmental oversight, China undercut rivals in price and built capacity at every stage of the supply chain. By 2009, the world was already feeling this shift. China supplied more than 96% of the world's rare earth elements and was on track to eclipse all competitors. The key industrial hubs were Inner Mongolia's Bayan Obo district, the world's largest rare earth deposit, and Biotu, where vast tailings lakes of toxic sludge bear witness to the environmental costs of separation processes. Then came September 22, 2010. A Chinese fishing trawler collided with Japanese Coast Guard vessels near the disputed Senkaku Diaoyu Islands in the East China Sea. Tokyo detained the captain, and within days, Beijing responded with an unexpected economic hammer. It halted exports of rare earths to Japan. As China's export quotas had already been slashed earlier that year, down 72% in July from the previous year, this embargo sent shockwaves through global supply chains. Japan, at the time, depended on China for roughly 90% of its rare earth imports. With its high-tech and automotive industries reeling, prices for key materials soared. Samarium, indispensable for missile guidance systems, tripled in price to around $32 per pound. Japanese manufacturers scrambled to diversify, investing in new mines and recycling technologies, and the world began to wake up to a peril few had foreseen. Despite a World Trade Organization complaint by the United States, European Union, and Japan, and a 2014 ruling that found China's export restrictions violated trade rules, the episode had already achieved its strategic effect. Countries realized they could not allow one power to dominate rare earth supplies without risking enormous leverage being placed in Beijing's hands. By the mid-2010s, China had entrenched that leverage even further, consolidating its rare earth industry into state-backed giants such as China Northern Rare Earth Group and, later, The China Rare Earth Group formed through massive mergers in 2021 and 2024 to tighten control. Throughout, Western mining industries faded. The United States' principal rare earth mine at Mountain Pass, California, struggled. It closed in 2002 and only reopened later under new ownership, but its output could not match China's scale. Meanwhile, European producers found themselves priced out or unable to compete with the combined weight of Chinese subsidization and integrated refining capacity. China's dominance is not just in raw ore, but in the whole industrial chain. By the mid-2020s, roughly 70% of global rare earth element mining, 92% of refining, and 98% of rare earth magnet production was rooted in China. These magnets are critical because they are the heart of electric motors, wind turbines, and advanced electronics. A 2025 analysis by Goldman Sachs warned that even a 10% disruption in rare earth element supply could result in up to $150 billion in lost global economic output and drive inflation in sectors dependent on these metals. During the escalating U.S.-China trade tensions under President Donald Trump, rare earths again became Beijing's weapon. Trump's tariff offensives in 2025 prompted Beijing to tighten export controls on 7 key rare earth elements, including dysprosium and samarium, and to impose licensing requirements that could delay or restrict shipments of critical components abroad. These moves were officially framed as national security measures, but the strategic messaging was unmistakable. China could throttle materials essential to Western clean tech and defense industries if pushed. And it worked. Trump backed off. China is already a rising power. And this episode proved it perfectly well. China's military modernization and its global ripple effects. On a gray morning in Beijing in November 2015, President Xi Jinping stood before senior officers of the People's Liberation Army and announced that China would undergo the most sweeping military reforms since the Mao era. The goal was to build a force capable of fighting and winning modern wars. What followed over the next decade was a systematic modernization driven by materials, electronics, data, and scale. At the heart of this transformation sat a resource most people never think about: rare earth elements. China's monopoly in rare earth mining gave it a structural advantage in producing advanced systems at scale. This advantage became visible first in missiles and sensors. The PLA rocket force, elevated to a full-service branch in 2016, rapidly expanded its arsenal of precision-guided weapons. Systems like the DF-21D, often dubbed the world's first operational carrier-killer ballistic missile, and the longer-range DF-26, designed to threaten U.S. bases in Guam, rely on advanced guidance, radar, and electronic countermeasures, all rare earth-intensive technologies. China was not just fielding missiles, but building layered sensor networks, integrating satellites, over-the-horizon radars, and electronic warfare units into a single kill chain. Air power followed the same logic. While much attention in the West focused on China's stealth fighters, the J-20 Mighty Dragon, which entered operational service around 2017, a quieter but equally important story was unfolding around a less glamorous aircraft, the Chengdu J-10C. The J-10C is not China's most advanced fighter. It is not stealthy like the J-20, nor as heavy as the J-16 strike fighter. But that is precisely why it matters. The J-10C represents China's shift toward network-enabled, sensor-fused combat. Introduced in the late 2010s, it features an AESA radar, modern electronic warfare systems, data link connectivity, and compatibility with China's latest air-to-air missiles, including the PL-15. The PL-15, with an estimated range exceeding 200 kilometers, is powered by an active radar seeker and advanced propulsion, again, dependent on rare Earth-based components. By the early 2020s, China had hundreds of fourth- and fifth-generation fighters in service, supported by domestic supply chains insulated from foreign pressure. Unlike many Western programs plagued by cost overruns and limited production runs, China emphasized scale and speed. Then, the ripple effects began to spread beyond China's borders. One of the most closely watched cases was Pakistan, China's long-standing strategic partner. In 2021, Pakistan officially announced the acquisition of the J-10C, marking one of China's most significant exports of a modern frontline fighter. By March 2022, the first J-10C squadron was inducted into the Pakistan Air Force, stationed at Minhas Air Base. The aircraft were paired with Chinese munitions, including the PL-15 missile, giving Pakistan capabilities it previously lacked. The timing mattered. Pakistan's regional rival, India, had just begun inducting Dassault Rafale fighters from France, widely regarded as among the most capable non-stealth fighters in the world. The Rafale brought with it the RBE-2 AESA radar, the Spectra electronic warfare suite, and the Meteor missile, often described as the gold standard of beyond visual range combat due to its no-escape zone. On paper, India's Rafales represented a decisive qualitative edge. For several years, they were treated in regional and Western defense commentary as a stabilizing counterweight to Pakistan's numerical advantages. That assumption was severely tested in May 2025. India and Pakistan battled it out in the air. This was the most intense aerial confrontation between the two nuclear-armed states in decades. Over several days of rapidly escalating engagements along and beyond the line of control, both air forces surged fighters, airborne early warning aircraft, and surface-based air defenses into a dense, contested battle space. Pakistan bagged a victory by downing multiple Indian aircraft, including Rafale. Chinese technology, previously assumed to be inferior, had clearly outperformed a top-tier Western aircraft. Believe it or not, rare earth dominance played a huge role here. This allows China to produce advanced electronics without supply disruptions. State-backed defense firms can iterate quickly, absorb losses, and manufacture at scale. According to U.S. Department of Defense reports, China now fields the world's largest navy by number of ships, a rapidly expanding air force, and a missile force central to its regional strategy. On the flip side, the USA is still dependent on China's mining industry. Well, not for long. America's rare earth vulnerability and strategic risk. The United States, the most technologically advanced military power on Earth, has a quiet but critical weakness. It no longer controls the materials that make its weapons work. The irony is that the United States once dominated this field. In the 1980s and early 1990s, the Mountain Pass mine in California's Mojave Desert was the world's leading producer of rare earths. American companies refined, separated, and processed these materials domestically. But rare earth processing is chemically aggressive, expensive, and environmentally messy. As environmental regulations tightened and cheaper Chinese production entered the market, U.S. producers shut down. Mountain Pass closed in 2002, and with it went not just a mine, but decades of technical know-how. China filled the vacuum. By the time American policymakers realized what had happened, Beijing controlled the choke points: refining, separation, and magnet manufacturing. Mining was only part of the story. The real vulnerability lay in processing. By the early 2020s, China handled over 90% of global rare earth processing. That meant that even when the U.S. mined rare earths domestically, they often had to be shipped to China for refinement. This reality triggered an alarm inside the Pentagon. In 2018, the U.S. Department of Defense formally listed rare earth elements as critical to national security. Subsequent reports warned that a supply disruption could halt production lines for missiles, aircraft, and naval systems. The Department of Energy echoed those concerns, identifying rare earths as part of a broader set of critical minerals vulnerable to foreign control. These warnings came as U.S.-China relations were deteriorating. During the Trump administration's trade war, China openly signaled that rare earth exports could be restricted. State media reminded audiences, domestic and foreign, that rare earths were a strategic resource. America's most advanced weapons relied on materials controlled by a geopolitical rival. Inside defense circles, planners ran scenarios. What happens if exports are delayed? What if licenses are denied? What if access is throttled during a crisis? Unlike oil, rare earth supply chains cannot be rerouted overnight. Processing facilities take years to build. Skilled chemists and engineers are not interchangeable. A disruption measured in months could ripple through weapons production for years. The vulnerability extends beyond defense. The same rare earth magnets used in missiles are also essential for electric vehicles, wind turbines, medical imaging machines, and consumer electronics. This creates a competition between civilian and military demand in any shortage. A Department of Energy analysis in the early 2020s warned that surging EV adoption could strain rare earth supplies even without geopolitical pressure. So why hasn't the United States simply rebuilt its rare earth industry? Because rebuilding is far harder than dismantling. Mining rare earths in the U.S. faces economic, regulatory, and environmental hurdles. Opening a new mine can take a decade or more, requiring federal, state, and local approvals. Processing plants involve handling toxic chemicals and radioactive byproducts. This raises legitimate environmental and public health concerns. China absorbed those costs early. Western democracies struggle to balance strategy with environmental standards. There are also cost issues. Chinese producers benefit from state subsidies, integrated supply chains, and economies of scale. Competing on price is difficult without government intervention. When Mountain Pass restarted operations under new ownership in the late 2010s, it still lacked domestic refining capacity and had to ship concentrate abroad. Recognizing this, Washington began to act. Between 2020 and 2024, the Pentagon and Department of Energy awarded hundreds of millions of dollars in grants to support domestic processing, magnet manufacturing, and recycling. Companies were incentivized to build separation facilities in Texas, California, and the Midwest. Japan and Australia became key partners, particularly through firms like Lynas Rare Earths, one of the few non-Chinese processors operating at scale. But even optimistic timelines stretch into the late 2020s. Supply chains built over decades cannot be replaced in a few budget cycles. What worries strategists most is not just dependence, but strategic asymmetry. China does not need to completely cut off rare earth supplies to gain leverage. Even uncertainty, delays, inspections, and licensing requirements can raise costs and inject hesitation into planning. In a crisis, the mere threat of disruption becomes a bargaining chip. This undermines long-term strategic autonomy. Military planners prefer certainty. They want to know that production lines can run during conflict, not just in peacetime. Dependence on a rival introduces doubt into every calculation. Can surge production be sustained? Can damaged systems be replaced quickly? Can allies rely on U.S. resupply if America itself is constrained? The American dilemma is now clear. The United States still designs the world's most advanced military systems. Its engineers, software, and operational concepts remain unmatched. But without secure access to the materials beneath that technology, dominance rests on unstable ground. This is not a crisis yet. No production lines have stopped. No weapons programs have collapsed. But strategists understand the difference between peace and stress. Supply chains that function in calm conditions can fracture under pressure. Rare earth vulnerability is the kind of risk that only becomes visible when it is too late. and that is why it haunts Pentagon briefings. But maybe there's a way out. The discovery in America's polluted waters. On a quiet stretch of creek in West Virginia, the water runs the color of rust. It stains rocks orange, kills fish, and smells faintly metallic. For decades, locals knew it as poison. What almost no one realized was that beneath the surface of those polluted streams lay something the United States had been desperately searching for. There is a history lesson here. For more than a century, coal mining powered American industry. When the mines shut down, especially after the 1970s, they left behind thousands of abandoned shafts and tunnels across West Virginia, Pennsylvania, Kentucky, Ohio, and Virginia. Rainwater seeped into exposed rock, reacted with sulfide minerals like pyrite, and flowed back out as acid mine drainage, or AMD. The chemistry is brutal. The water becomes highly acidic, often with a pH as low as 2 or 3, similar to vinegar or lemon juice. That acidity dissolves metals from underground rock, iron, aluminum, and manganese, which then spill into streams. By the early 2000s, the U.S. Environmental Protection Agency estimated that more than 5,500 miles of streams in Appalachia were polluted by acid mine drainage. Entire watersheds were effectively dead. States spent millions each year trying to neutralize the water with limestone and chemical treatment systems just to stop the damage from spreading. Then, quietly, scientists started noticing something strange. When AMD is treated, the process is simple in principle. Operators add alkaline materials, often lime or sodium hydroxide, to raise the pH. As the water becomes less acidic, dissolved metals fall out of solution and form a thick, muddy residue known as treatment sludge. For decades, this sludge was considered waste. It was hauled away, stored, or buried. But around the mid-2010s, researchers analyzing that sludge noticed unexpected signals in lab tests. Alongside iron and aluminum were trace amounts of rare earth elements.
Did you know that one of the largest rare earth mines in the world is in California?
It's in the San Bernardino community of Mountain Pass.
At West Virginia University, researchers at the National Research Center for Coal and Energy, working with funding from the U.S. Department of Energy, began systematic studies of acid mine drainage sites across Appalachia. They sampled water and sludge from abandoned mines like the Richard Mine and Long Fork Mine in West Virginia. What they found surprised even seasoned geochemists. In some locations, the concentration of rare earth elements in AMD, once concentrated through treatment, was comparable to grades found in traditional rare earth mines overseas, particularly ion adsorption clays in southern China. The water itself held low concentrations, but the chemistry of acid mine drainage had already done the hard work. It dissolved the metals naturally, without blasting, crushing, or chemical leaching. You see, rare earths behave differently depending on pH. In highly acidic water, they stay dissolved. As pH rises during treatment, they selectively precipitate out. By carefully controlling the treatment process, adjusting pH levels in stages rather than all at once, researchers could cause rare earth elements to separate into a distinct metal-rich fraction within the sludge. Pilot projects funded by the Department of Energy demonstrated a two-step chemical process. First, the acidic water is treated to remove bulk contaminants like iron. Then, at a higher pH range, rare earths precipitate out more selectively. The result is a concentrate far richer than untreated sludge, compact, transportable, and ready for further refinement. Researchers then pushed the process further. Using solvent extraction and ion exchange techniques, the same fundamental chemistry used in conventional rare earth refineries, they refined this concentrate into high-purity rare earth oxides, achieving purities of 95 to 98% in laboratory and pilot-scale demonstrations. This mattered enormously. Traditional rare earth mining is destructive, generating massive earth disturbance, radioactive waste, and toxic tailings. By contrast, acid mine drainage recovery offers a striking alternative. The polluted water from abandoned coal mines already contains dissolved rare earths, and treatment systems exist to neutralize it. This approach turns environmental cleanup into a potential source of strategic materials without new mining. By 2021, the U.S. Department of Energy identified AMD, coal refuse and coal ash, as domestic rare earth sources, reframing Appalachia from an economic casualty into a strategic asset. Challenges remain. Sites are dispersed, chemistries vary, production must be scaled, and downstream infrastructure for magnets and alloys is limited. Legal and economic hurdles persist, and China's dominance still looms. Yet even modest domestic recovery strengthens national security. It also reduces reliance on foreign suppliers, and it transforms polluted streams into assets. The United States may have a chance against China after all. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.